These are the notes for Unit 1. So this is day 2. We're going over units and measurements. We're going to start talking about units. Really, the units that we use in this class are based on the metric system, and we really call them SI units. So it's like the International System of Units. It's pretty much just the metric system. Okay. Now, there are two types of SI units. First, we've got a base unit. A base unit is the simplest single unit for a measured quantity. Can y'all read that? Okay. Yes? Okay. So it's just going to be a single unit. A derived unit is a unit that comes from multiple other units combined. So most of the time, a derived unit is going to be when there's like some form of math or something involved. Most of the time, that's how you're going to get a derived unit, and that's how you're going to get multiple units involved. Okay? So we're going to start talking about mass. So whenever we are measuring mass, what are we actually measuring? Yes, it's the amount of matter. So I do use a lot of abbreviations whenever I write because I'm lazy and I don't feel like writing out the full word. Whenever I introduce a new abbreviation, like I'll make sure that we know what it is, but if at any point you're reading what I wrote and you're like, I have no clue what that means, please ask me. I'm happy to explain it, okay? Most of the abbreviations I use are common and you've seen them before, like amount. I'm pretty sure like a lot of y'all have seen amount abbreviated AMT, okay? But if you don't know what it is, please ask me. So yeah, mass measures the amount of matter. What do we use whenever, like what do we use to measure the mass of an object? Yeah, so it's going to be a scale or a balance. I mean, they're the same thing, just different words. Okay? The unit that we use in science for, like, it's the metric system, SI, okay? We use kilograms and grams. What is the symbol for kilogram? kg. What about gram? G. Okay? And then do you think that mass is a base? So whenever we measure mass, that unit, is that base or derived? Yeah, it's a base unit. Good. We're just measuring how much matter is present. Okay. Length. Whenever we're measuring the length of something, what are we actually measuring? Okay, width, length, anyone? Those are all like, yes, however, like those don't tell us specifically, like what we're really measuring is the distance. So like the distance between one point and another. So like the distance between like this side of my paper and this side of my paper. Yeah, I'm measuring like the width of it, but it's still the distance between 2 points. What are we going to use to measure length? Yeah, we're really going to use rulers. Like we don't deal with anything long enough to require a meter stick. But yeah, you could use a meter stick, but really we're just going to use a ruler. Okay, those units that we're going to use most often, meter and centimeter. What's the symbol for meter? M, and centimeter? cm. Perfect. Do you think that's base or derived? Base. Wonderful. Okay, let's talk about time. Whenever we measure time, what are we measuring? So think about like when we're in a lab, okay, and we have to measure, like we have to measure time, okay, like we're using something to measure time. What are we like thinking about? Like what are we actually measuring? Yeah, duration. How much time has elapsed? So oftentimes we're going to, like, it'll be like, okay, how long did it take for this reaction to happen? Right? So it's going to be time, like time elapsed or duration, something like that. We're not reading time as in, like, what time is it? We're reading, like, how much time has passed during this point. Okay, what are we going to use to measure time? Stopwatch. Yeah, stopwatch. I'm going to put a timer, but, like, stopwatch, timer, I mean, you can even use a clock, okay? If at any point we need to use, like, we need to measure time in here, we'll, like, tell you what to use. But, okay, the unit for that is seconds, so we don't measure time in minutes here. We use seconds. What's the symbol for seconds? Good, it's just S. So you might have seen seconds abbreviated as SEC before, but once we get into, like, this level of science, we use just S. That's what they use in physics, so that's what we use in chemistry, just S. Okay, and then is this going to be base or derived? Base. Okay, let's talk about temperature. Whenever we measure temperature, what are we measuring? Okay. Yeah, tell me your name. Okay. Yes, it is actually, we're actually measuring the speed of the molecules of that substance. However, the speed of the molecules is actually the average kinetic energy of those molecules. Temperature is actually average kinetic energy. The hotter something is, the faster those molecules are going to be moving. Okay? How are we going to measure temperature? Yeah, thermometer. Okay. Our units for temperature are Kelvin and Celsius. Whenever we're actually measuring temperature in the lab, our measurements are going to be in Celsius. That's what our thermometers are going to give us. However, sometimes we are going to have to use Kelvin, but we'll do a conversion to get to Kelvin, okay? Because Kelvin is actually measuring, like, that kinetic energy, okay? We can, like, we're never going to have, like, 0 kinetic energy, right? But we can have, like, 0 Celsius. So we have to do a conversion to get to Kelvin, okay? And we'll learn about that later. What do you think the abbreviation for Kelvin is? Yeah, capital K. What about Celsius? C. We're going to do degree C. Kelvin does not use a degree symbol, okay? You'll just see that for Celsius. Okay, is this going to be base or derived? Base. Perfect. All right, now we're going to talk about volume. What are we measuring when we talk about volume? Yeah, it's the amount of space an object takes up. It's the amount of space an object takes up. That is the volume. What might we use to measure volume? Okay, a beaker. Anything else? Graduated cylinder, yeah. So I'm going to say graduated cylinder, but you can definitely use a beaker. Graduated cylinder is going to be a bit more like precise and accurate, but you can definitely use a beaker to measure volume for sure. What else might we have to use? What if it's not a liquid? How do we measure the object, like the volume of like a solid? Like, how would you measure the volume of like a cube? What would you do? Yeah, you'd have to use, like, you'd have to get multiple, multiple measurements. What would we use to get those measurements? Yeah, so you can use a graduated cylinder. You might have to use a ruler. And I'm just going to put, like, etc. To say, like, beakers, like flasks, those kind of things can also be used to measure volume. It's not just these two, but you get the gist. Okay? So, whenever we're measuring things like liquids, we're going to use liters and milliliters as our units. What are the abbreviations for those? So, capital L, and then what? Yep, ml. Okay? Whenever we're talking about solids, we're going to use like meters cubed or centimeters cubed. What would that look like? m cubed, and cm cubed. Okay. Do you think this is going to be a base or derived unit? It's not going to be both. What, base or derived? Yeah, it is actually derived. How do we know that? Yeah, so this is technically, this here, like meters cubed or centimeters cubed, is actually technically multiple units. It's the same unit, but it's there multiple times. Okay? Why do we think, so that's why there, but this isn't multiple units, right? Why do you think, like, this is still going to be a derived unit, but anyone want to take a guess as to why, like, even though this is one unit, it's still derived? Yeah, it's three-dimensional. So your graduated cylinder, your beaker, whatever you use to measure that liquid, has actually already done, like, the calculation for you whenever they put the markings on that container. So then all you have to do is just measure it. So they've already done, like, those calculations for you, and then we're just going to use one unit for it. But technically, it is taking 3D space into account. Yeah. Great job. Awesome. We got two more here. Next is density. Whenever we talk about density, what are we actually referring to? Yeah, so compactness, specifically what? Yeah, so mass over volume. What is mass? Amount of matter. What's volume? Amount of space. So we're going to say it's the amount of matter in a given space. Also known as, like, how compact are the molecules? How close are the molecules together? Okay. So if we need to measure density, what equipment do you think we're going to need? Yeah, we're going to need a scale, right? Because we're going to have to measure the amount of matter. So we're going to need a scale. Anything else? Yeah, like a graduated cylinder or a ruler. Grad cylinder / ruler. And again, I'm going to put like ETC, like etc. down here to say like you don't have to use specifically these, but like you get the gist. We're going to have to use something to measure the mass and something to measure the volume. Okay, the units that we'd use for that is grams per milliliter and grams per centimeters cubed. What are those going to look like? G/ml and G/cm cubed. Do you think it's base or derived? Derived for sure. We have different units here that should like more than one type of unit that automatically should tell you it is a derived unit. Okay, last one is something kind of really specific to chemistry, and I actually mentioned it last class when I talked about like our mole money, okay? We are going to use mole pretty much every single unit for the entire year, okay? Mole is a very important unit in chemistry. Has anyone like heard of it before? Anyone know what it is? Yeah, go for it. Yeah, what were you going to say? Same thing? Yeah, so don't write this down yet, but mole is a unit that basically tells us the amount of molecules, the amount of atoms, whatever that is, in our substance, okay? However, whenever we're referring to that chemical, there are going to be a lot of particles, a lot of molecules, atoms, whatever it is, okay? So we're not going to want to refer to specifically how many molecules are there. That's going to be a lot. Instead, we use a mole to make it just an easier number for us to discuss and do calculations with, okay? So a mole, what it does is it measures the amount of a chemical. Okay? And whenever we talk about moles, like I said, mole is an easier number to use to talk about amount of particles. The amount of particles in a substance is called Avogadro's number. Okay, so whenever we talk about moles, Avogadro's number is all, like, most of the time we're going to use it. Okay? Avogadro's number is 6.022 times 10 to the 23. So for every 1 mole of any substance, there are going to be 6.022 times 10 to the 23 particles. It has to do, like, yes, but you don't have to worry about it right now. So literally all you have to do is just know that Avogadro's number is that amount of particles, and that always is 1 mole of that substance. So that number you are going to know in, like, you're going to have that memorized in a couple units because of how often we use it. However, technically you don't have to memorize it. So it's actually on your formula chart. So on your formula charts that you got, under constants and conversions, it's listed right here. Avogadro's number equals 6.022 times 10 to the 23 particles per mole. So if we've got, like, multiple moles of a substance, you can understand why we want to talk about it in terms of moles and not particles. Because if we're dealing with, like, 3 moles, it's this times 3. We don't want to have to, like, write that out every time. We instead say 3 moles. Okay? So like I said, you never have to memorize this, but odds are it's probably, like, you're probably going to memorize it just based on the frequency that we use it. Okay. And then how do you get moles? Well, it's actually done with calculations. So you have to, like, you have to calculate something like you're converting from, like, particles to moles or whatever it is. Okay. The unit is a mole. Okay. And then there is actual, like, there is a symbol, there is an abbreviation for mole. It is, in fact, MOL. We've saved you so much time by making you not write the E. You can check over your stuff even more now, right? So mole is MOL. Feel free to write out fully MOLE or MOL, same thing, okay? And then do y'all think this is a base or a derived unit? Who thinks it's base? Who thinks it's derived? Oh, I love the 100% participation going on here. No, it is actually a base unit. Because yes, while technically we're using calculations, we're not actually, like, using multiple units. What we're doing is just converting particles, number of particles, to moles, which is just an easier number to digest. So, like, here, we're dealing with, like, meters. If we wanted to convert from meters to centimeters, would that make, even though we're doing a calculation, would that make this a derived unit? No. It'd still be a base. So that's why here, like, for moles, we're not combining units, we're just converting them. And so, yeah, even though we're doing calculations in math, it's still going to be a base unit. Okay, any questions about units? Anything on this first page? We good? Okay, cool. Awesome. So flip to the next page, and we're going to talk about accuracy versus precision. Does anyone actually know, does anyone off the top of their head already know the difference between accuracy and precision? Yeah, tell me your name. Yeah. Okay, and tell me the difference.
So, like, precision would be, like, even if you're not hitting, like, the middle, you're still, like, hitting them all in the same area. But accuracy is if you're, like, not hitting them all together, but you're just hitting the middle.
Yeah, great. Like, that is a great explanation. So precision means that, like, all of your data points are very close together, whereas accuracy means all of your data points are close to the true value. Okay? So, accuracy is how close the measurements are to the accepted value. However, instead of accepted, sometimes you might see true, actual, or known. Any of those you might see instead of accepted. They all mean the same thing, value. Okay? Now, we determine how accurate this, we determine accuracy usually through this calculation. It's usually calculated with percent error. This W slash, that means with. That's a common one that I use. So W slash means with. I'm going to use that abbreviation a lot. Okay? So accuracy is usually calculated with percent error. Okay. Precision, we're going to talk about precision in two different ways. First is what we just discussed, like talking about data. Okay, so if we're talking about data, it's the repeatability in experimental data. So how close were your values each time you ran a trial? Were they close together? Were they similar? Or did you get a huge variety? The more precise you are, the closer your values are to each other. However, we're also going to talk about precision in terms of equipment. So how precise a piece of equipment is. So when we're talking about equipment, we're saying how many place values can be recorded. So if we have two different pieces of equipment, okay, we're measuring the volume of a liquid. One of them, we are able to say, okay, this looks about 25 milliliters, okay? However, another piece of equipment, we're able to say, okay, this looks like it's around 25.6 milliliters. What do you think is going to be more precise? 25.6. You're able to write out more place values, so you're able to be more precise with your measurement. Yes? Okay. So this is a good visual representation of accuracy versus precision. Okay? This first one, what do you think it is? Yeah, this one's going to be accurate. Okay? They did a really good job of getting close to the bullseye. Okay? However, they technically weren't precise because, yes, while they got one in the bullseye, the other four, they got on like all four corners of it. Okay? They weren't like compactly gripped. So this was just accurate. What do you think this is? Yeah, neither. They weren't precise or accurate. Okay? Yeah, they got one in the bullseye, but the rest of them are spread all over the place. This might be me if I'm throwing things at a bullseye. However, odds are I probably wouldn't even hit it. So, what about this one here? Yeah, this one's both. So, they were accurate. They got all of them in the bullseye. And they were precise because they are all grouped together inside that bullseye. They were all really close together. What about this last one? Yep, just precise. They weren't anywhere close to the bullseye, but they were all grouped really close together. Okay, so that's like a nice visual representation. However, that's not really how we reference accuracy and precision here in chemistry. Whenever we talk about accuracy and precision, almost always we're going to be referring to like data values. So let's take a look at this table. So Michael and Amy measured the length of a pencil 3 times, and they got the following data. The manufacturer says that the length of the pencil is 19.0 centimeters. Okay, so Michael measured the pencil 3 times, Amy measured it 3 times. Who had the most accurate measurements? Michael. How do we know it's Michael? Yeah, he's closest to the actual value, okay? And while we can look at it here and get a pretty good idea because, like, he got it exactly and then 0.1 off on either side, okay? Sometimes we're going to get data values that aren't that clear to be able to determine if they were super accurate. If we've got multiple data points and we can't really tell, what do you think we might do to determine? Yeah, you're just going to take the average. So what's the average of Michael's measurements here? 19.0.
But then, does that mean you can have 18 and a 20 that would make it exactly accurate?
Yeah, you could.
Even though that's less accurate than 80?
Well, but the thing is, like, he took the, like, over all of his, like, whenever he averaged each one, he was still more accurate, but he was gonna, like, he's less precise. So, we might take the average, if we're looking at who was more accurate overall, we're gonna take the average. However, oftentimes, we will specifically, like, take the, like, determine accuracy or percent error based on a single measurement. However, if you're given a table and you want to know overall who was more accurate, you're going to take the average. Okay? And then who was more precise? Amy. What was her average? 18.2. She got the same measurement each time, but it was not nearly as close as Michael's. Okay. Questions? Awesome. So when we talked about accuracy, and most of the time we're going to refer to accuracy using this percent error calculation. Okay? So percent error is a calculation that's used to determine if the measurements are accurate. Okay, so we're going to calculate a percentage. Do you think that we would want a smaller percent or a larger percent if we're looking for accuracy? Smaller percent, because we're measuring percent error. We want a lower error, right? So the smaller the percentage, the more accurate it is. Smaller the percentage, the more accurate. Okay, you're going to use two numbers to calculate the percent error. The accepted value and the experimental value. So the accepted value, that's that known value. Or it might be like the reference value. Okay, that is what is known to be true. The experimental value, that's your lab measurement. So that's whatever you got in the lab. That's what you measured yourself. Okay? So if we go back to this table, what is our accepted value? Yeah, this 19.0, that's our accepted value. Okay, what's the experimental value or values? Yeah, whatever's in our table. So these are the experimental values that's in the table. Okay? To calculate it, you're going to take the accepted value minus the experimental value over the accepted value times 100. Okay? But what are these like tall like bars here? Absolute value. What does that mean?
Distance from 0.
Distance from 0, so we don't care like which direction it's distance from 0. So really what that means is we're just going to make everything positive. So we're just, percent error is always going to be positive. The hardest thing when calculating percent error is just identifying what's your accepted and what's your experimental. That's going to be like the most common mistake that you make. Okay? This is the formula. You do not have to memorize it. It is, in fact, on your formula chart. So over here under data analysis, you've got percent error right here. Okay? So what I want you to do is on the next page, I want you to do this first example. So go ahead and try and calculate that. Okay, so whenever you are doing math problems in here, whenever you're doing calculations, in order to get credit, you got to show me your work. Okay, so you're going to write out the work that you're doing. Okay, most of the time, so if it's a simple calculation like this, we don't grade, like your work isn't worth a point. However, you don't show it to us, then you're not going to get the point even if your answer is correct. Okay, so make sure really all you have to do is just show me the numbers plugged into the formula. Okay, so what would that look like? Okay, if you wanted to put the absolute value, you could, but I don't really care here. Okay, so whenever we do this, what would we get? 11.43, 11.4%. That's fine. Okay. If you write out percent error, that's fine, but really, like, all you have to do is put percent. Okay, so this would be your final answer. How do we feel about that? Yeah? Literally, all you have to do is identify which value goes where in the formula, plug it into your calculator. Okay. I'm going to skip this one. If you want, like, a little extra practice, you can, but, like, I feel like y'all got this. So, okay. Now we're going to talk about precise in terms of glassware, precision. So, out of these pieces of glassware, what do you think is going to be the most precise? Yeah, the graduated cylinder. So this is the most precise. Thanks. So this is the most precise. Why are we saying this is the most precise? Yeah, so more place values, more tick marks, really. It just comes down to, if you've got more tick marks, it's going to be more precise. Except if we're talking about a volumetric flask. And I'll talk about that in a second. Okay? Which of these is going to be the least precise? Yeah, the test tube. So it's going to be the test tube, because honestly, this one doesn't even have markings on it. I don't know where here is 10 milliliters. Is it like where it says 10 milliliters? Is it the very top? Is it like right here? Who knows? This is the least precise. Okay, so when we talk about volumetric flask being the most precise, that's because, so, out of all, out of all glassware, the most precise is a volumetric flask. Okay? And this is different because a volumetric flask actually only has one line on the whole thing. However, that line is so precisely, correct. Like, if you put it at that line, you are measuring exactly what that volumetric flask is supposed to hold. So if you've got like a 200 milliliter graduated or volumetric flask and you pour, get it up to the line, that is so precise. Okay? We don't use it to measure volumes. Okay? We use it to hold a very specific volume. Okay? So, volumetric flasks are the most precise piece of glassware, but it's not going to be the most precise if we want to record how much we have. Yes? Okay. All right, so let's talk about recording measurements real quick. So, guidelines. Whenever we record measurements, whenever we're going to identify what that measurement is, how much we have, we're going to always report known digits plus one estimated digit. So, for example, and you're always going to write your units. So, for example, A here. If we were to measure A, we know for sure it is at least what? It is at least 0.5. But can we say it's 0.6? No. So we know it is at least 0.5, so we can go ahead and write 0.5. However, are we able to guess how close it is between 0.5 and 0.6? Yeah, we can make a guess, right? So if we were to read this, what might we say? It's 0.52. Yeah. So we'd say 0.52. The 0.5 is our known digit. We know it's at least 0.5, but it's less than 0.6. The 2 is our estimated digit. We don't know for certain that it's 0.52. It could be 0.53 or 0.51. That 2 is our estimated digit. Once we estimate a number, that's where we stop. So we would not try and do 0.521. We would stop at 0.52. Yes? Okay. So looking at, let's see, D. What would we say D is? Yeah, we could say 2.51. I'm going to say 2.50 because to me it looks like it's exactly on that line. Okay? To me it looks exactly on that line. So I know for certain it's 2.50. However, I still can't say with certainty that it's not 2.51. My estimate is that it's 0. Okay? So that's what I would record. Because these only measure to the tenths. I can't say with certainty the hundredths place, so that is always going to be my estimate. That's where I stop. We good on how to do it with a ruler? Yeah? Okay. It is the exact, pretty much the exact same when we talk about glassware. Okay? So glassware, however, we talk about precision, the precision limitation of a glassware. The precision limitation is that estimated digit. So it's the place value of your estimated digit. So last digit, you are allowed to report. And it's that place value. So, on your ruler, the last digit we reported was in the hundredths place. So our precision limitation is the hundredths. So for glassware, that's our estimated digit. However, if it's an electronic scale, that's just the last digit displayed. We can't make an estimate on an electronic scale because we can't tell, okay, this here, we can't tell if this is 0.001 or if it's 0.002. We can't make an estimate there. So if it's electronic, we write just whatever it says. Okay, so when we talk about actually reading equipment and putting that into practice for graduated cylinders and scales, it's going to look really similar. So this one here.
Good afternoon, Trailblazers. The time is now 4:30 and the...
So this right here shows that, so this is 30. This is 40. So we know that our meniscus is past, so this is 35, 36, 37. We know that it is past 36 and it hasn't reached 37 yet. So we can go ahead and write down 36 because we know that it's at least 36, but it hasn't reached 37 yet. And then when we read graduated cylinders, we read from the bottom of the meniscus. So that's almost always going to be right in the center, the lowest parts. So to me, if I were to read this, this looks a little more than halfway between 36 and 37. So I might report it as 36.6 milliliters. And the precision limitation, so reminder, the precision limitation is the last digit that we report, specifically the place value of that digit. So the precision limitation of this recording is going to be the tenths. Because the last digit we recorded is in the tenths place. So we are precise up to the tenths place. Whenever we are dealing with electronic equipment, we're not going to estimate that digit. So the recording here is 0.0 grams. The precision limitation of that, again, is going to be the tenths, because that is the last number that we wrote. That last 0 is in the tenths place. Okay, so go ahead and try this graduated cylinder on your own. I'll give y'all a second. Pause the video and then come back whenever you finished it. Alright, so we're going to do the recording of A. So A is this top one. So we know that this is 30 and this is 40. So we're going to go ahead and count the tick marks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know that each of these is worth 1. So this is in between the 37 and the 38th tick mark. So we can record A as 37 point, and then we're going to make an estimate. So I would say this is probably, I might say this is 37.9 milliliters. Looking at B, B is down here. So B is at 1, 2, 3, 4. It looks like it's exactly on the 35 mark. So I know it's exactly at 35. So I know it's at 35. And it looks like it's exactly on the mark, so I'm going to estimate that it's 35.0 milliliters. Again, I'm not completely certain about that 0, but that is my estimate. So the precision limitation of this graduated cylinder would be the tenths, because that's the place value of the last digit that we wrote for each of those recordings. Okay, so if you remember when we were going over equipment last class, we were talking about how burettes are a little different than graduated cylinders. So burettes go backwards. So it's not necessarily that we read them backwards, it's that the numbers are written backwards. So we're still going to go 10 to 20. However, we're going to go down. So this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay? So this is not 20.5 or whatever it is. This tick mark right here is 15. So our initial recording, you can go ahead and say like 15 point, actually it looks like it might be a little above that mark. So you can either put 15.0 or 14.9. I'm going to go ahead and just put 15.0 milliliters. And then our final recording. So this is 15, 16, 17. It's past the mark of 18, but has not reached 19 yet. So we can say the final recording is 18 point something. And it doesn't quite look halfway. I might say it's like 18.3 milliliters. It is not 21.8. It is 18.3 because we're reading down. Okay? And if we wanted to determine how much liquid was delivered, so how much we sent out of our burette, all we would have to do is take our final minus our initial. So we do 18.3 minus 15.0. And so we're going to end up with about 3.3 milliliters. Now, we understand, oh, sorry, one last thing. Our precision limitation, again, is the tenths place. All right, now we understand that when we read these, not everyone is necessarily going to get the exact same number. I said this was 37.9, but someone else might read it as 37.8, okay, or 30 or 38.0, okay. We normally give y'all a plus or minus 1 buffer on each side. So if I read this as 37.9, I would accept 37.8 and 38.0. So it'd be a plus or minus 1 buffer of the last number that we record. All right, that is the end of day 2. So please, if you have any questions, come see one of us. Our tutorial schedule is posted on Canvas. Otherwise, I hope y'all have a great rest of your day, and do not forget, you have a lab next period. So come ready to have fun, but make sure you're wearing closed-toed shoes. Have a great day.